So if these are the two first partial derivatives, then I showed you also that we could find second partial derivatives, right? And the second partial derivatives will both come from, we'll have one set of partial derivatives that will come from this first partial derivative, and then we'll have another set that will come from this partial derivative. So if I wanted to take or find the second partial derivatives, first you can find, if I want to find the partial derivative of the first partial derivative with respect to x, then this is how it's notated. And I take the derivative of the first partial derivative with respect to x, I do that with respect to x. So what would that derivative be? Let's see. So this is the only term that has an x in it, so it would be 2y, right? The derivative of x to the first is just 1. And then the derivative of this term is 0, the derivative of this term is 0. Okay? Now, if I want the second partial derivative of x with respect to y, make sure that you don't take the derivative of this term. I've mistakenly done that before. You have to go back up to this first partial derivative. You see the subscript is x and then y. That means the second partial derivative, the first partial derivative with respect to x, and then the partial derivative of that with respect to y. All right, so we go up here and we do that, and so that's going to be 2x, right? The derivative of this term with respect to y is just 2x. That's going to be 0, and then that's going to be what? Plus 9y squared. All right, so we have done half of the second partial derivatives. So these two here that I'm highlighting, that's the two first partial derivatives. The second partial derivatives, you have to take the partial derivative of each first partial derivative with respect to both x and y. Okay, so now I'm going to come over here and I'm going to find the partial derivative of the first partial derivative with respect to y. So that's going to be 0, that's going to be 0, and that's going to be 18xy. Okay. The question now is, where did I make my mistake? Let's see. 2xy minus 3 minus 3x squared. Or did I make a mistake? Let's see. 0, 0. I don't think I did. Okay. You know how I can tell if I made a mistake? It's the very last thing I told you on Friday. And here it comes right here. So I need to take this second partial derivative with respect to x. So this is the partial derivative with respect to y and then respect to x. So again, don't go to the previous line here. This was the second partial derivative with respect to y. I need to go up here and take the derivative of this with respect to what? X. So that's going to be 2x plus 0 plus 9y squared. Now, what up here kind of jumps out at you? Something should kind of jump out at you and say, hey, man, what does that always happen? We have two of those second partial derivatives that are the same. F sub xy and f sub yx. They're both the same. Remember what I called these here? They had a special name. Mixed partial derivatives. Mixed partial derivatives are always equal. Okay, so that's kind of a way that you can check, right? Now, on Friday, whenever we were working this, I showed you how it could be used. You know, if you have a function in two variables, you can figure out maybe the if we were talking about first derivative, meaning velocity, then we could find the velocity like maybe in the x direction, in the y direction, things like that. Also, there were a couple of alternate notation techniques we went over. You can write the first, I'm just going to show you this real quick. Since I said z equals f of xy, and I know we went over this on Friday, but this is just a little review. You can write, to find the first partial derivative with respect to x, it could be written like this. Sometimes you'll see it written like this. It means the same thing. So if I'm formally giving a definition, I may write it like this. But if I'm working it out and I just don't want to write as much, I want to use a shorthand, I'll just write it like this. If you know that z equals this function, then you may also see it written the partial derivative. This is the partial derivative sign right here. It kind of looks like a script D or a 2 that just isn't quite right, but it's the partial derivative of z with respect to x. So all three of these mean the same thing. This is the partial derivative sign right here. Sometimes in definitions or especially in differential equations, you may see that. Yeah. All right. So that's about where we left off. I told you that mixed partial derivatives were equal. We did not do many partial derivatives with 3 variables. I did show you that you could have a function of 3 variables. Let's say that I have f of x, y, z equals y e to the x plus x times the natural log of z. I don't think we've worked this one. Let's see what we would have to do to show that f sub x z, that's the second partial derivative, first partial derivative with respect to x, second partial derivative with respect to z, is equal to f of z x. So let's not find all the partial derivatives. Let's just show that those two are equal. Because by definition, mixed partial derivatives have to be equal. So what we would want to do, we want to first find the partial derivative of f with respect to x. So any term that has an x in it is what we're looking at taking derivatives of. We have to hold the y and the z constants here. All right, so the derivative of the first term, we're taking the derivative of e to the x. Well, the derivative of e to the x is e to the x. So that's y e to the x. Second term, derivative of x times natural log of z. Well, when we're taking the derivative of the x, the natural log of z is a constant. We may not be used to thinking of natural log of z as a constant, but here it is. So I take the derivative of the x term, and that leaves me with natural log of z. So it's just plus natural log of z. All right, so we want to find f sub x z. So we need to take the derivative of this with respect to z. So f sub x z, this is the second partial derivative. All right, so what would the derivative of y e to the x be? We don't have a z right there, do we? So that's all a constant when you're taking the derivative with respect to z. So it's just 0. Plus the derivative of the natural log of z. It's just 1 over z, right? 1 over z. The derivative of natural log of z is just 1 over z. And then the derivative of z is 1, so you don't have to worry about that. All right. So that's f sub xz. Now let's find f sub zx. So we need to first find the first partial derivative with respect to z. So the first term doesn't have a z in it, so that's 0. The second term does have a z in it, so this x is a constant. The derivative of the natural log of z is 1 over z. So that's just x over z. Right? Now let's take the derivative of that with respect to x. So this will be f sub zx. Second partial derivative incoming. So this is what? This is x times 1 over z, really. You may not always think about it like that, but you may want to break it up like this so that you can see that it's 2 terms, but it's really just the x times 1 over z. So the 1 over z, that's a fraction. You can think of it like it was a third. Well, a third times x, if you take the derivative of 1/3 x, it's just 1/3. Well, it's not 1/3, it's 1 over z. So the derivative of this, derivative of x to the first is 1, leaves you with 1 over z. Okay? So you can see those two mixed partial derivatives are equal. Now here's what I want you to do. Let's take this a little bit further. Let's see if f sub x z z is equal to f. It should be equal to every type of combination of these three. So it should be equal to f sub z x z, and that should also be equal to f sub z z x. These are third partial derivatives. We have 9 third partial derivatives. We're only going to find these 3. But of course, you may have to find some of the second partial derivatives we haven't found already in order to find these. So I want you to take a minute and do that and see if those 3 are equal. Alright, so let's first do, I'm going to do this f sub x z. Alright, so the derivative of 1 over z, that's z to the negative 1. So it's negative z to the negative 2, or negative 1 over z squared. Now this one here, same thing. Now this one, so I gotta take this, and take the derivative of that with respect to z. So it's gonna be negative x over z squared. Derivative of that with respect to x is negative 1 over z squared. Alright, so all 3 of these are the same. just real quick now, we're going to go over some stuff that you already know. I'm not going to spend a lot of time on it because I know everybody in here has had physics or in physics or it's not or had linear algebra, and it's kind of, you know, it's basically what we were doing before the break with vectors, except a third dimension. So, you know, adding vectors, multiplying a scalar times a vector, finding the magnitude of a vector, all of that stuff is the same. We all know that in 3 dimensions, of course, we don't have ordered pairs, we have ordered triples. So if I had 2 points, let's say x sub 1, y sub 1, z sub 1, and x sub 2, y sub 2, z sub 2. If I wanted to find the distance between those 2 points, then we would just use the distance formula. This is one of the first things that's covered in 11.2. I mean, it's so easy that it's not difficult at all. So it just depends on what your points are, right? You'll say x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared plus z sub 2 minus z sub 1 squared. So let's see if you can, real quick, find the distance between 2 points. Let's find the distance between these 2 points here. So I got a distance of 3 square roots of 3. And so, what does this actually give us again? This gives us the distance between 2 points, right? Now, what if I made this point here my center point, and then in 3 dimensions I went that same distance out in every direction in 3 dimensions? What would that give me, right? What would that give me? Think about it for a second. I was going in every direction. I went that same distance. And what would that kind of give me there? What do you think? That'd give me a sphere, wouldn't it? So we can use the distance formula to come up with the equation of a sphere, the standard equation of a sphere, because of the way that a sphere is defined. So if you let the middle point here just be like your center, say it's our initial point, x sub o, y sub o, z sub o. We're going to call that the center of the sphere. Then the equation of our sphere would be x minus x sub o squared plus y minus y sub o squared plus z minus z sub o squared equals r squared. Right? If we took our formula, and of course we can think about these points any way we want. I just made, it would be like making your second point, I guess, your the center of your sphere. And if we took the collection of all of those distances, all those radii, I guess you could, that's what they are, all those radii in the 3 dimensions, like this is the z, this is the x, this is the y. Then we would have a sphere. Here's a prettier sphere. It's kind of hard to draw a sphere. Your book does a little bit better job than I do. If you shade it in certain areas. So we have our center here, we have a radius here, and then in all 3 directions, in your x, your y, and your z directions, that the distance from the center of the sphere to the outside of the sphere is the same. We could find the midpoint of any radii the same way. You just add the 2 x's together and divide by 2. Add the 2 y's together, divide by 2. Add the 2 z's together, divide by 2. How would we find the equation of a sphere if I gave you 2 points, maybe the center and any point on the outside? So let's find the equation of the sphere in standard form that has the points -5, -2, a negative is crazy, 3, and 0, 4, -3 as endpoints of a, let's make this a little tougher. Let's think about it, of a diameter. So what is a diameter? So diameter would just be, you know, if you look up here at this sphere where we have this point and this point, well, what if I gave you this length here all the way across? So we have one point here, we have one point here. We need to first figure out the center of the sphere. And so if I gave you this point and then some point over here on the other side, how would I find the center? How would I find that point in between? How would I find the midpoint? Yeah, just add the x's together, divide by 2. Add the y's together, divide by 2. Add the z's together, divide by 2. So that would be 5/2. That would be, what would it be, 37? No, it'd be 2, right? Is it 2? Yeah, 1. Okay, somebody was doing that right. All right, good. And then what would the last one be? 0. So that's the center of our sphere. Let's look up here again now. We need to understand what we're doing. I gave you 2 endpoints. I didn't give you this middle point up here. I gave you this point and I gave you this point. And I said, here's 2 points that are on the ends of the diameter of a sphere. Let's figure out the equation of the sphere. So if you find the midpoint, you find the center, because diameter means all the way across. Ever since the 5th grade, it has meant all the way across the circle. Right, well, we're just taking it into 3 dimensions. All right, so we have the midpoint formula. Now, what do you think that we need to figure out? If we have the midpoint, that's going to be our what? Think of it in 2 dimensions or 3 dimensions. Come on now. I know you don't like to talk. I don't like to talk to myself. Well, I do like to talk to myself. But we just figured out this point here. But this is a 3-dimensional object. But we figured out that point there. So now, I know the center. What else do I need? The center. I know my x sub o, my y sub o, and my z sub o now. What else do I need for my formula? The radius. So how do I find the radius? The radius is the distance from the center to either endpoint. So it doesn't matter which endpoint we use, we can find the radius. Let's use the one that has a 0 in there, because that makes at least one of my numbers easier to work out. So I'm going to use this point here because it has a 0 in it, and I like zeros. I like to give them out as test grades. And then we have to use this right here. This is our center. So if we go from the center to either point, I'm just going to use this one, then we'll have, if we find that distance, then we'll have the radius. It doesn't matter which one you think of as x sub 1, x sub 2, x sub 3. Just make sure, or x sub 1, y sub 1, z sub 1, just make sure that you think of one of them as the first point, the other as the second point. It doesn't matter which way, because you're taking the difference and squaring it. Alright, so the distance, or the radius, is going to be equal to the square root of, let's say, I'm going to let this one up here be my first point and this be my second point. So I'll have, it doesn't matter though, you're going to get the same answer. 0 minus 5/2 squared plus 4 minus 1 squared plus negative 3 minus 0 squared. Alright, so that's going to be the square root of Negative 5 half squared, that's 25 over 4, plus 9 plus 9. Alright, so I need this in fourths, so that's going to be 36 over 4 and 36 over 4. 36 and 36 is 72. 72 plus 25 is 72. 97. So that's a square root of 97 over 4. How should I probably write that? I guess that's fine. You can simplify that to the square root of 97 over 2. But this is fine too, because remember what you have to do, the radius, whenever you write the formula of a sphere. What do you have to do to the radius? Square it, right? So let's write the standard form of the equation of this sphere. We have the center, that's the center right there. So it's going to be x minus 5 halves, that's 5 halves squared, plus y minus 1 squared, plus z minus 0 squared. So that's z squared equals, now what do you get when you say the radius squared? Any more of that? 97 over 4. So that is the equation of a sphere that has a diameter with endpoints 5, negative 2, 3, and 0, 4, negative 3. We figured out the midpoint. That gave us the center of the sphere. Then we used the center of the sphere and one of the endpoints to find the radius. You could use the other endpoint. You could use this center and the other endpoint and get the same radius. If you don't, we did something wrong. Alright. So just like we think about a sphere in 3 dimensions, which you've probably done before. If you haven't, it's very similar to a circle. We can think of a vector in 3 dimensions. So if we have a vector, remember what a vector is, right? We've got to have 2 endpoints. All right, so if we have a vector v, instead of having 2 components, that vector will have 3 components. V sub 1, V sub 2, and V sub 3. Now each one of those components usually is, like the difference, if you have 2 endpoints, the difference there from one endpoint to the other. You say the second minus the first, or first minus the second, or however you're looking at it, and get your vector. All right. The 0 vector, of course, would be what? Would just be the ordered triple. I mean, if you have 0, that's going to be 0, 0, 0. You can kind of think of it like a triple. It's a triple. It's 3, right? Not 2 anymore. If we have 3 dimensions, then what would the unit vector I be equal to as an ordered triple? Remember, we had written it as just a ordered pair. We had written it as 1, 0. That was before the break. As an ordered triple, it would simply be 1, 0, 0, right? That's in 3 dimensions. These are unit vectors. These are standard unit vectors. Okay, what would J be equal to? 0, 1, 0. All right, very good. And does anybody know the one in the third dimension, that we use for in the direction of z? That's k. We use k. So k is equal to the ordered triple 0, 0, 1. So for any vector v, the standard unit vector notation for v, and I know I'm using a lot of terminology, but written as a linear combination of those three, the standard unit vector would be v sub 1 I plus v sub 2 j plus v sub 3 k. So for example, if I have a vector v equal to 2, negative 3, 6, then I could write, and I'm trying to put a little terminology together, I could write a linear combination of those three components. You could write it as, that's 2i minus 3j plus 6k. Is that usually how you would write that in physics? Do you write it in both forms? Do you write it in this form and this form? Or usually just as the ij and k? Ij and k, yeah. Remember though, for any one of these components, what are these components made of? They're made of 2 points. So each component comes from 2 points. I'm not trying to confuse you, I just want to remind you. Like if we have 2 points, say one point P that has 3, and this isn't a vector, this is a point. Say it has P sub 1, P sub 2, P sub 3. So that's like a X, a Y, and a Z. And then you have another point, Q, and you may not need to write this down, you may just understand it. You have Q sub 1, Q sub 2, Q sub 3. So that's like a X, Y, and a Z. Then where do these components of the vector come from? They come from these 2 points. The actual vector, V, which is made up of V sub 1, V sub 2, and V sub 3, where do those V sub 1, V sub 2, and V sub 3's come from? They come from that difference, Q sub 1 minus P sub 1. That's the first component. And then Q sub 2 minus P sub 2. And then Q sub 3 minus P sub 3. So you always need to keep in mind that a vector does come from 2 points. Now it may have direction and magnitude and all of that, but each component is made up of at least 2 points. All right, well that's where we're going to stop today. So.